So hi everyone, my name is Joey and this is Josh, and today we'll be talking to you about writing a Polyglot Datastore story. If any of you guys are playing the container drinking game, this is not the room for you. You'll be unfortunately sober at the end of this talk. However, there are lots of talks after this with lots of containers, so it'll be okay. All right, cool. So let's start off with a little bit about what Yelp is. If you haven't heard about us, we're a company that connects people with great local businesses. We have an app and a website and stuff. Lots of users, lots of data, tons of reviews, check-ins, and all of this is user contributed. And naturally, we therefore have a lot of databases. Lots of different kinds of data stores for dealing with different use cases. We have three general classes that we like to talk about, but really there are only two here. We have what we call sources of truth. These are databases that we kind of like trust with our users' data. When we get a write to one of these data stores, it's kind of like, okay, cool, we trust that it's actually there. And then we have derived stores like our search indices and memcache, maybe our analytics databases. These tend to be derived off of the sources of truth. And oftentimes they'll go through one of our streaming data stores like Scribe or Kafka or some message queue.
So Joey, there were like 12, I just lost count. So there are so many data stores on that other slide, and people at this conference are just telling us about how we should be minimizing our surface area of support. Why do all this work?
Yeah, so the secret answer is don't do this. Don't have lots of data stores unless you have to. I mean, as engineers, we should all be really pushing to minimize the amount of complexity in your architecture. But sometimes you have a lot of really good reasons for adding complexity. For example, maybe a core competency of yours has to do with data stores. If you're a search company, you probably care about search engines, and you really need to be able to fine-tune them. So like, for example, Yelp's a search company, and we handle transactions. And we do lots of fun things that require us to really understand the consistency, availability, trade-offs, like, I mean, whatever, cap theorem is boring and everything. But we do have to care about that. So we have to care about that. We have to care about performance. Can we scale it? Like, yeah, maybe you can do 1 million writes today, but can you do 10 million writes tomorrow? And maybe you're just having a service-oriented architecture that requires lots of services, and those service authors come to you and are like, well, we need to be able to do all these crazy things. And you're like, oh my God, I don't know how to make my SQL do that. So sometimes there are good reasons to do this. So our talk is primarily going to be about how to do that, and a little bit of history for how Yelp got there. Josh will take over here.
So yeah, starting around 2011, we have these 5 major data stores. They look pretty familiar to most people who operated a web stack in 2011. You can see we had things for relational data, things for search, and some log structured and deferred job processing. And we had 1 data center, 80 developers, and 1 real service. So 2012 rolls around, we're getting new data stores. 2 new ones, Zookeeper and Elasticsearch, both filling in niches that were not filled by the previous data stores. And we have more data centers now, more developers, and 5 real services. We're starting to dip our toes into service-oriented architecture. And then 2013, 2 more data stores, Kafka and Redshift, and we have twice as many data centers, now at 4, 200 developers, and we've gone SOA, we're now at 30. And 2014 rolls around, Cassandra and Dynamo add to our story again, and we now have 6 data centers, 400 or so developers, and if you didn't believe we were SOA before, now we have 100 services. So, oops, we SOA'd, we added a bunch of complexity, we added a bunch of data stores, we went from 1 service to 100.
Wait, why did we do this again?
I think the answer to that's centralized around developers and the features that those developers have to support. So developers are responsible for features. Those features need services. And the services need data. And the services need data in different ways based on the service. Data is actually what is creating a lot of value for our company. And data is hard. Is it easy?
No, it's pretty hard.
Oh, shit. So each one of these data stores is good at something we need. Each feature on the website, except the ones that are entirely static, is enabled in some way by one of the data stores here.
This seems like it's going to be pretty hard to maintain going forward.
Yeah, but that wasn't a question, really. But yeah, you have to plan ahead. For us, it's worth it to enable these features. It means good things for our business. So we now have a flock of data stores. How do you tend to them? I think there are 4 major ways that we need to consider that one tends to a flock of data stores. First is education. We need to educate developers and operators about the data stores that they use and the ones that they're responsible for. Also, we need to think about deployment and configuration. We need to support hundreds of these data stores, each one with its own configuration. And we need to support this diversity without ever saying, oh, well, we snowflake that in right there. Or, oh, that's just that one that we never think about ever. We need to support each data store as a first-class entity. We also need to think about monitoring. We need to be providing a suite of tools that allows developers to monitor the data stores that are backing their services. And finally, we need to consider good abstractions. We need to provide these data stores to developers in a way that provides a good API for them while preserving flexibility for operators.
Cool. So the first step of this is education. And we can't say this enough. If you're adding a new data store to your Polyglot data store story, one of the very first things you need to do is educate yourself and educate others about that data store. And this starts with research. So if you guys haven't heard of Afer, he's written some really great blog posts. But the key takeaway for me from these blog posts about data stores is that you shouldn't believe what data store vendors write on the box. Because the reality is that when you try to take their data store and put it in production, something is going to go horribly wrong. So one thing that we've definitely learned is that be skeptical of data stores, but that doesn't mean don't use them. It just means verify that they do what you think they do before you really roll them out everywhere and make your application thoroughly dependent on them. But once you decide to do a data store, you're going to have to commit to maintaining the education for that data store going into the future. And something that we kind of bring this education into three main categories. The first one is written education, and we do this through documentation. You should make sure that you have good example code for your developers, good runbooks for your operators. If they're the same person, they're both important. And finally, take the lessons that you've learned from stoifying, from taking your services and throwing them in containers and all that stuff. But take that and apply it to your data stores. You should be writing postmortems when somebody misunderstands the performance characteristics of an inner versus outer versus, I don't know, actually NoSQL. He's the guy that knows SQL. But you should be writing postmortems and educating your engineers continuously. But furthermore, some people don't don't learn as well from the written word. Some people really like oral communication. So we found that lectures, lightning lectures, and actually longer lectures can be really, really helpful for this. Some of them are given by engineers on their own team. They're like, hey guys, I just learned how to data model in Cassandra. I'm going to show you some things that I learned. Those can be like little 5-minute conversations, or maybe Josh and I gets up and gives like a 40-minute presentation about how you should always choose one thing for a particular application. But the point is that we mix these together and we use them to build a network of experts. And we do this through things like office hours. Something that we do is our data store experts on any given team actually hold office hours for other developers to come ask questions. So I can go ask Josh what's the difference between inner and outer join, and he'll take like 45 minutes to explain it to me, and it's fantastic. Afterwards, I maybe forget it, but that's okay. Then, of course, we have IRC channels. And HipChat or Slack or whatever, you should definitely make sure that you're using chat as a way to build this network of experts. So let's give some concrete examples. This is an example of our Elasticsearch documentation. Definitely write down your documentation. It evolves, and one of the things I love about this is that it shows that it evolves. At the very top there, it's like, hey, this page this replaced is like over here. It's super old and wrong. Don't listen to it, right? I'm the documentation that's actually authoritative. So treat your documentation like your code. It has to evolve with your code. But furthermore, make sure your documentation has trade-offs. So this is one of the things that I think is really important, is at the beginning of any documentation, we always say, when should you be using this data store? Should you be spinning up a new cluster? Should you be using an old cluster? Should you not be using Elasticsearch at all? These are questions that you need to answer. These are questions you need to have answers for. As for lectures, I would say the big takeaway there is record them. Because if you record your smart engineers giving presentations, then when new hires come on, they can either use the documentation or those lectures as learning material. You don't have to give the same presentation 14 times. And finally, if you want to write data correctly the first time, make sure that you record your chat conversations. Some of the best design discussions that happen about data stores, about like when you should use MySQL or Cassandra or whatever, some of the best conversations happen in chat. And I don't care if you're using Slack or HipChat or whatever is hip and cool these days, just make sure you record it and you can search it and surface it when people have these questions. Cool, so all of these things work together to build expertise. And this kind of comes back to Yelp's core philosophy about data stores, which is that developers should be getting their hands dirty. And I mean, I think that we've all taken it for granted with the DevOps revolution and stuff, that okay, operators and developers, they should be working together. But sometimes we still have those DBAs that we're like, okay, well, the DBAs will tend to the databases. It's like, no, developers need to get their hands dirty with databases because it prevents a pretty bad scaling problem for your organization. where you end up with a centralized team of experts. Instead at Yelp, what we've done is we've built a distributed team of experts where everybody has some knowledge. And what I hope that you take out of this is that think about the developers around you on your teams. Hopefully they can explain what SQL is, why indices help. If they're using Elasticsearch, they should maybe know the difference between a term and a filter. And these are things that every developer who's using those data stores needs to have some level of education on, because they're very core to your business. Cool. So we've decided they're important, but how do we actually deploy them?
Well, we should consider a couple ways. First, we'll divide up deployment and configuration. For configuration, Puppet is our trusty configuration management tool. We use it for so many things. In general, the box should be coming up without any human intervention, and we'll cover how we make that possible as further on in the presentation. But for the start, just basic things that Puppet deals with is disk partitioning, configuration files for your data store, setting up the processes that are going to run the data store and any helper processes that are necessary, and configuring whatever monitoring we have on that machine. And we need to support variety. We have all sorts of data stores. One Elasticsearch cluster may be very different from another. One might support site search. Another might support an ELK cluster. And they're going to have different feature sets, different guarantees, and in general, they will need to be configured rather differently. So we need a scalable way to handle these differences. And the one we settled upon was Hiera. It's actually a really good tool. It's a hierarchical data store that is built into Puppet. So we set up a Hiera hierarchy for each data store in question. As you can see here, we've got Kafka, MySQL, Cassandra, Gearman, and Zookeeper, each one with its own hierarchy. And we'll give you an example in a second. Puppet experts in the room might also notice that this is not typical for Hiera. This is per module Hiera data. There is a Hiera data hierarchy in each Puppet module. So here we can see the example as applied to Cassandra. If you're sitting up close, you can see that the default cluster is at the bottom of the hierarchy. The default cluster is every default that is just for any Cassandra cluster. Above that is the versions defaults. These are, say, Cassandra adds a new feature in one version, or we want to use a specific option in the latest version that perhaps wasn't fully baked in previous versions. That would go in versioned defaults. And there's a file for, say, Cassandra 2.1.1 for these defaults. And then there's a per cluster file. So each Cassandra cluster will have a YAML file just of its own for its specific settings. And here's an example of one of those per cluster files. We can see that the search infra team has this Cassandra cluster configured for them. They're actually allowed to log in and admin the box. They have their Cassandra version that Puppet will install, specified right here, and they have some storage configuration tweaks that are just for their cluster. And using this architecture, we can support whatever that cluster needs, just with different toggles and settings in this file. So a little bit a more complicated example is Elasticsearch. You can see the bottom 3 levels of the hierarchy are relatively similar: the defaults, the version defaults, and then the clustered level defaults. But there's also this concept of a node role. So in Elasticsearch, we'll have some nodes that are master nodes. They won't handle data. Other nodes that are data nodes that don't handle shard allocation. But we have a YAML file for each one of those, but we can extend this functionality to whatever we want. If one day someone said, oh man, I have this excellent idea for a widget Elasticsearch role, we can just create a widget.yaml within the node roles for that Elasticsearch cluster, and suddenly any node that is tagged as a widget role will launch with that configuration. And this is special to me, I think, because I have experience with MySQL where previously we were just snowflaking things on a per hostname basis. So there was no guarantee that one host would come up like another, because one hostname might have a number of overrides that made it a special snowflake. In these cases, with this example, there's no such thing as a special snowflake. There's just the widget role, and the widget role can be brought up any number of times. So here's an example with Elasticsearch. You can see it's very similar to Cassandra. You can see that this one's for the ad delivery team, and they've configured a number of very similar options. And you can also see that, say, they have 3 plugins that they want installed. We should also consider the things that Puppet isn't going to do for us. Puppet's an excellent, excellent general purpose tool, but it's not really designed for health checking or managing dynamic cluster membership or getting data onto a machine. These should be the jobs of other tasks that can run for long periods of time, unlike Puppet, which should have single runs that last short periods of time. So we have a couple of tools that we've built or repurposed for this purpose. So for load balancing and cluster management, we have SmartStack. SmartStack is a general purpose application load balancer that we also find works really well with datastores. For health checking, we have SmartStack, HACheck, and Sensu, each one providing a different component of monitoring. And lastly, for data bootstrapping, we either have custom tools or we have the tools that are built into the data store that just ship out of the box. So to give you a little bit of idea about the SmartStack tool that I mentioned a moment ago, it's a load balancing system. And the way it works is that on each backend service, there is this nerve process that does health checking. And the nerve process health checks, in this case, say a Cassandra node, and upon seeing that it's passing health checks, writes an ephemeral node into Zookeeper saying, this backend is available at this host and port. And that's great. Synapse watches Zookeeper and sees a new entry, and then reconfigures an HA proxy on each box that is going to be a client to that backend. So as you can see here, the control plane is entirely separate from the data plane. The client connects through the local HA proxy using the fat blue lines to go to the backend, and SmartStack doesn't have to get involved in the data layer. Our clients don't have to be recompiled or monkey patched to have this new functionality. It's just a co-process that is providing this functionality out of band. And this is really powerful, but you might be saying, Josh, Cassandra, Elasticsearch, they do their own cluster discovery. Why would I go through HA proxy? And we thought the same thing. We had SmartStack going up, but instead of just throwing out the tool because it works really well for us, we instead taught Synapse, Joey taught Synapse, how to write JSON files instead of HA proxy configuration. So with that functionality, we can just have Cassandra or Elasticsearch be configured to Cassandra or Elasticsearch clients connect to their backends using these JSON files. And that's been really powerful for us. It means that our clusters are almost entirely dynamic. We don't have to do much curation of, oh, well, this host went down, so I need to update my seed nodes or something like that. SmartStack handles all of that for us. And now that we've got that done, we have to consider okay, well, data stores need data, right? Yeah, okay. Data stores need data. So we need a couple ways to get data onto those data stores. First way is find a way not to do it. So as an example, memcache fills itself over time. You just bring up a new one and point your application at it. There are also those situations where it's mostly handled for you. Elasticsearch and Cassandra, once you have the cluster discovery working correctly, they will handle their own shard and partition allocation. So that's excellent. But you also need the cases where MySQL comes up and it needs data. And we don't want to have to make this a human-mediated process. So we're going to make some custom tools to provide data bootstrapping for MySQL. With our tooling, what we do is we have existing servers responsible for serving snapshots of the MySQL dataset to new servers that come up. The new servers are responsible for finding existing servers with the dataset, requesting a snapshot, automatically restoring those backups, and bringing up MySQL and making it healthy. So now we have clusters, and they have configuration, and they have data. But we have to consider a little bit how many clusters should we have? How should those clusters be split up? And in resource isolation, there are so many ways to do this. I think our ultimate goal is to prevent clients from hogging resources. But there are different approaches that we can take. The first is to share resources. So Yelp was founded, I think, 2005, and MySQL was the thing, and you deployed a single MySQL box for your tiny service, and it was shared infrastructure. And as MySQL grew up, we largely took that approach. In Elasticsearch, it was sort of the opposite. It was, let's shard out the resources as much as possible, so there will be a number of clusters, each one completely isolated from the others. And then there are, of course, middle grounds. There are ways to have different use cases share resources without making everything centralized or everything distributed. And all of this is dictated largely by our monitoring considerations. So we should consider those monitoring considerations. Fires happen all the time. These two data stores on this slide have managed to be healthy somehow. I don't know why. Distributed systems are failing all the time, but four of them in the single tenant case and one of them in the multi-tenant case is completely on fire, which is the norm for distributed systems. So when fires happen, how are you going to figure out what they are? And that's the job of our monitoring. So for us, we split up monitoring we allocate clusters based on who's going to carry the pager for them. The pager will be handled by the team responsible for the cluster in question, the team supporting the feature that this cluster provides. And it doesn't really matter what you use. Like, we use Sensu, and it works great, but you can use Nagios. And I think it's actually super important, though, that you provide a number of ways to get in contact with people, a number of ways to notify them, hey, something might be awry. So for us, that means chat, so people can get IRC messages saying, oh, BT dubs, your cluster might be a little unhealthy. Or there's email, same thing. There are tickets, and there's actually paging someone, like sending something to the PagerDuty API saying, please wake this person up. Lastly, you can call a CEO, but I don't recommend doing that, nor do we do that at Yelp. So a couple considerations about when to ticket, when to page, what is the low priority sort of stuff, what's the high priority sort of stuff. So for us, lower priority sort of stuff is, okay, we've recognized something weird, but it's not going to immediately hose some feature or bring down the site. So MySQL is at 10 seconds of replication delay for more than 2 hours. I'd say that's a problem. Maybe file a ticket about it so that people who are, as they check their email, can say, yes, I have some context. Maybe something's a little wrong. Elasticsearch is in a prolonged yellow state. That's a problem. Maybe we should inform someone. Cassandra just lost local quorum, and you're reading local 1. OK, let someone know via a ticket. Zookeeper is 1 node away from not having a quorum. It's also a problem. Let someone know. Things are about to be unhappy. File a ticket. Let someone know. Now let's think about when to freak out, when to page someone. So MySQL is at 60 seconds of replication delay. Why don't we page someone? Elasticsearch just entered a red state. Cassandra lost local 1, and Zookeeper just lost quorum. Things are really, really unhappy. We should let a human know. But you can see that all this is calibrated to provide condition monitoring of, hey, something might be wrong, in the way that is least likely to page someone out of bed, least likely to disrupt someone's life. And lastly, an important component of not disrupting someone's life is trying not to monitor single hosts. For these distributed data stores, it's really easy. We can say our service is provided by the entire distributed data store, and we never have to monitor a single host. So why would you? Hosts fail all the time, and your sleep is important. So we monitor the cluster as a whole and the service it provides. Lastly, these metrics that the data stores report are super important. When something is wrong, or when you're diagnosing a performance issue, or when you simply say, do I have headroom, we need to have these metrics available. And so each data store that we deploy has a rather robust set of metrics that allow us to dig into, OK, how's my performance doing? What's my query latency look like? All of these things that developers and operators alike are going to need to make intelligent decisions.
Yeah, so we just learned about how to build the right abstractions and make sure that every data store we deploy fits into the right abstractions for operators and people who are deploying data stores. But you also have to have good abstractions for developers. And that comes down to kind of this, which is that ideally your developers are thinking about two main abstractions, writes and reads. They want to write data to some data store, and they want to read it back. But unfortunately, reality tends to be a little bit more crazy. You tend to have logic, which is writing into your sources of truth. It's also maybe doing a side write over to a derived data store. Then you have some offline batches, which might be reading from one and writing to the other. And this is what we found at Yelp is that this is actually really hard to maintain. But we can see kind of the light at the end of the tunnel when we can recognize that there are two kinds of data in an infrastructure. There are sources of truth. These are things that we really, really care about, like MySQL or Kafka or Zookeeper. These are things that the user is interacting with. And then there are all these derived stores, which we can rebuild at any time, right? Like I can rebuild my search index, or I can recover from losing that index for a few hours. I can rebuild that. That's no problem. So what we can do is we can kind of reduce this picture a bit, and we can try to be really strict about whenever we're thinking about data, we think about it as either a source of truth or derived data. And then we can capitalize on this fact that we already have an abstraction for how to get data from sources of truth into derived data stores. But this is really fundamentally important because your derived data tends to be most of your data. Think about your infrastructures, right? Like, is most of your data in like that users contributed, or is most of your data like you taking that and putting it in some kind of index, or taking that and throwing it in an analytics database, or maybe you're logging a bunch of stuff? So if we can solve the problem of how do we reliably build derived data from sources of truth, then we can go a long way in making our infrastructure better for developers. Let's quickly change segments though and go to reads, which also tend to be a bit crazy, right? Like I have logic, I have services, maybe like so we show one logic block here, but you might have like 100 microservices which are reading from all different kinds of data stores. Maybe they're doing like server-side joins and things, or sorry, service-side joins, and it's really kind of sad. And we're going to go ahead and say that ideally you don't let services do that. Ideally, you put a query proxy or some kind of abstraction in between your services and your logic layer and the actual data stores that serve those data use cases. Sometimes. So this is obviously a trade-off. You're adding a proxy. Proxies always have trade-offs, and we can talk about those in a few minutes. But
so Joey, wait, you said like there's a query proxy, right? You're saying that I'm going to add another bit of operational complexity to my website. You keep saying this. Why are we adding so much operational complexity?
Yeah, we add operational complexity because this thing, change is a bitch, man. Like you're going to have to change everything about your data models. You're going to have to change schemas. You're going to have to change which version of a data store you use. A developer, I swear to God, is going to come to you and say, hey, I know you just rolled out Elasticsearch 1.2.1, but 1.2.3 just came out, and it has this awesome feature that I really need for my website, right? So you're going to have to upgrade versions. You're going to have to upgrade clusters. When Josh was talking about resource isolation, one of the best ways that you find out that, oh shoot, maybe we shouldn't have the payment accounts going through the same database that hold like the super big analytics queries is because something is going to blow up, and then you're going to have to move and partition that cluster. So you're going to have to be able to change which cluster provides a data API. You're going to have to change which client library to use, and you might even have to change data stores because features change. You might have said, okay, well, Cassandra will work really well for this, and 6 months down the line, someone's like, I want to add a full-text search component to this, and you're like, oh shoot, right? Like that's really hard in Cassandra. But we've got this other data store that does it really well. So as long as you can plan for change, then it's going to be worth it. So that's really why we take those abstractions. So let's kind of dive into this. Let's show you guys how we can plan for change and how we can build the right abstractions here. So first off, schemas. Let's talk about that. Because I can't tell you how many developers come to me and are like, oh, this cool new SQL database came out. I'm just going to throw unstructured. Don't do it. Have schemas. And the reason why you want schemas is because they are a contract with your data layer. It's a way for you to be able to change it later with confidence that the application code wasn't expecting some field to exist in that row or that document that you never even knew about. So have schemas, but be able to change them. You want to put them in one place, and you want to make sure you have good tooling to change them. So at Yelp, for example, like MySQL, we use PT Online Schema Change. There are lots of great tools for whatever SQL database you have. In the case of Elasticsearch, you can do version indices. In the case of Cassandra, luckily that data store comes out of the box with the ability to plan to change your schemas. But definitely have them. Because if you don't have them, then it's really hard to add them later. This is literally when your developer comes to you and is like, I want a new data API. You're like, OK, cool. Let's get a schema on it. Let's figure out what data you actually need. Cool. So that's the easy part. The hard part is being able to switch data stores. And if we can switch data stores, then we can solve all the other bullet points I talked about. be ready for being able to switch data stores, because the way that you can, some ways that you can do this are by recognizing data anti-patterns. So I'm going to go ahead and say that demand-filled derived data stores are pure evil for your ability to change them later. Because what it means is that in order for you to change that demand-filled data later, you have to go find all the applications which depend on that data and make sure that they, like let's say that you have two services which are both writing into some data store, then you're going to have to go change both those applications. And I don't know about you, but I don't want to have to go push 100 services in order to upgrade a client library or in order to change where they're writing their data. And this is where those abstractions come in, because the proxies really help you here, because you don't have to go push those hundreds of services. You can just change your proxy. All right, so cool. Let's talk about proxies. So we're going to use our proxies to change data stores in 2 steps. First, we're going to talk about writes, and then we'll talk about reads. And I already talked about this. This is going to be the abstraction that we're going to use. So now keep in mind that if we went back to that reality where we had like logic writing as derived data stores, this becomes very hard. But if we adopt this architecture, then we can pretty easily do this, because we only have one place that we know is responsible for taking data from a source of truth and reflecting it in a derived data store. So let's say that we want to upgrade from Elasticsearch 0.90.1 to 1.0.1. That's a major version upgrade that is a breaking API. So you've got to be pretty careful with this. But luckily, we're doing this offline in an ETL or something that's watching an RBR log, or in our case, we're using an indexer. So it's really easy. We just double writes. This is like pretty classic stuff. I know how to do this, right? But the key is that we're only doubling writes from one piece of code. We're not doubling writes from a bunch of different services or multiple places in one service within logic. Cool. So now we've got data in both places. Now we want to be able to do the real tricky part, which is switching reads. And the reason why I say switching reads is so tricky is because while you're doing double writes, your users aren't even noticing. But when you start switching reads, that's when your user can notice. Because that's when, if you do it wrong, they're potentially going to see all kinds of problems. So the way that we've solved this is that we put a big proxy in the middle. This is particularly useful because it allows us to make substantial changes to the left-hand side of this picture without the right-hand side knowing. So those application services and those developers who are deploying your web app, right, they don't have to know that I'm upgrading them from Elasticsearch 0.90.1 to 1.0.1, as long as I make sure that I maintain my contract with them, which for us lives inside this query proxy. So for us at Yelp, when a developer wants to use Elasticsearch or Cassandra, they don't put that code directly in their client. Instead, they put it in a query proxy, which has a fixed interface that is not the data store's interface. This is particularly important for data stores that are immature. So like MySQL's protocol layer has been fairly compatible for a while. But does anybody remember the thrift to CQL changeover for Cassandra? Was that fun? Yeah, how about the 0.91 to 1.0 Elasticsearch? I remember these ports. They were terrible because you had to go push all of your applications to use the new APIs that these data stores released. Whereas when you factor out that code and recognize, OK, I'm going to be changing this fairly rapidly and somewhat divorced from the service themselves, then you can do all those refactors all at once just in your query proxy. But furthermore, we're able to do this at Yelp because derived data stores tend to have most of the answer ready for you. This is kind of the idea of denormalization. The reason why you denormalize your data multiple times is to optimize so you only have to do one read out of your data store in order to serve a page. So you don't pay a lot of latency round trip costs with this. However, there are trade-offs there. Obviously, mileage may vary. Cool. This is especially good when you build lots of cool tools into your proxy. So for example, at Yelp, we use a query proxy called Apollo. We wrote a blog post about it. But the cool part about this is that in this picture, I'm showing you a single data API. So this is like, I want to search for reviews. OK, cool. Well, it used to be implemented with Elasticsearch version 0.90.1 with a client library that we call PyES, right? But we'd like to move it to a modern client library talking to a 1.0.1 cluster. Super easy. I just set up a MUX. Within the client, or within the proxy, I can just set up a real-time MUX that takes production traffic and splits it between 2 implementations. If I wanted to, we actually provide a lot of other things, like, for example, a comparison MUX, where you can send the request to 2 clusters and then compare the result to ensure that you're not breaking that functionality for your user. But finally, the thing that I think is really cool here is that we can do a dark launch. We can tee our traffic off to another implementation of this data API. So for example, let's say we want to try out a Cassandra cluster. We think, OK, well, we can back this data API with Cassandra much better than we can with Elasticsearch. OK, no problem. Spin up a Cassandra cluster, use those great bootstrapping tools, get some data in there, and then just write a little Cassandra cluster or a little Cassandra client in our proxy. No problem, right? And I mean, we don't have a lot of time today, but if you're interested, I talk a ton about the trade-offs involved in a proxy approach for derived data stores. Just anywhere you see the word Elasticsearch in this blog post, just change it for a derived data store. It's the exact same argumentation. Cool. All right, so we've switched over our writes, we've switched over our reads, we're reading to both places. All that's left now is to remove the old database. We're done. We just did a zero downtime change of a data store without our application developers freaking out because we had well-defined interfaces that allowed us to do acceptance tests against both different data stores and ensure that both of our implementations worked. Bonus points if you recognized that nothing I just said was specific to Elasticsearch. You could have switched to an entirely different data store, like Cassandra, to power the search API. And I think that's really the big power of those abstractions, is that you allow yourselves to rapidly iterate and change while not tying down your developers and requiring them to use what they've always used because it's hard to upgrade.
So hey, what should we take away from this? I think the first thing to take away is hold off on going Polyglot until you really have to. Fewer data stores is way easier to maintain than more data stores. Minimize your surface area of support, and you will be happier. But when those data stores are necessary, plan for diversity. You need to be able to provide a number of all sorts of functionality, and you need to be able to say, yes, I can support that. From the moment when someone says, hey, I have this rather weird use case, you can say, yeah, I can support all the diversity that is sensible. Cool. And then next, distribute responsibility. If some team has some really demanding use case that needs extremely low latency guarantees, a number of awesome things from this data store, say, OK, cool, I'm giving you the tools to do that, and it's your responsibility to make sure it works. And obviously, you'll help them along the way, but make one team's fire into their fire, and make sure that your resource isolation works to prevent it from ever being everyone's fire. And fourth, prepare for change. Your needs are going to change. Make your change easy, make it gradual, make it routine. It's safer and more efficient to have a comparison mux running in production for 2 weeks, 4 weeks, however long, a couple days, a couple hours, whatever, than to have to say, oh, well, we're going to take a maintenance window and we're going to need to be down and let's hope it works. Finally, one size fits some. We just gave you a bunch of info about how we do it at Yelp. We'll be happy to take questions. We'll talk to you more about it. But I don't expect everyone's use case in this room to be the same as ours. You should think of maybe the things that made this good at Yelp, and maybe also good at your organization, or maybe different for your organization. And with that is all. So we have a couple minutes for questions, and we'll be happy to take them. Yep.
So you guys have 100+ services. Were all of those centralized data stores, or do those services all have their own data store? And then how do you share things like users that need to exist probably in every data store?
Yeah, so in general, we try to adopt the single responsibility principle with services. So services are fully responsible for their data. But that doesn't mean that you can't have services which call other services that then manipulate data. So in the case of users, we actually keep most of the core shared data behind our main web app, and then services can ask the main service for things like users. But that's very much an architectural detail of Yelp. I'm not sure I would encourage that generally, but yeah.
Another question.
So you mentioned you use Lucene and Elasticsearch, and you need everything. Is there a reason you can't just use Elasticsearch?
So the question was, we have Lucene, we have Elasticsearch. They both do the same thing. Can we just use one?
That's a great question. That's a question. So I used to be on the search infrastructure team, and we asked ourselves that question constantly. We were like, why are we maintaining both of these? This is a nightmare. And the answer is that we started writing the search engine that's based on Lucene about 8 years ago, 9 years ago. So it has a lot of complexity and optimizations that are very specific to our use case. We definitely, from an infrastructure point of view, would love to run on just Elasticsearch. But from a development point of view, it would take us probably a year and a half to be able to actually port that functionality, achieve the same level of quality and the same level of performance.
We have the same thing, and it took a very long time.
Yeah, yeah. We basically we use Elasticsearch for real-time search, and then we can actually use our main search engine, which is based on Lucene, doesn't have full real-time search. It's like delayed by a half hour, and then it can look aside to Elasticsearch for like the little bit of data that we do need for real-time purposes. Cool. Any other questions? Oh, yeah, over there.
Last question.
Last question.
So you mentioned service level data joins and the code smell. So what can you get to, what kind of, like what do you look at when you have that kind of use case? Like what deeper kind of issues does that point to?
Yeah, so the question was, when you have service level joins, so like joins going on in service code, does that point to a more like fundamental problem or issue? And I think that the answer to that, I mean, do you have opinions on this?
I think it means that you haven't done a good job of synthesizing your data into a derived data store that will provide the answer to that query without requiring a service level join. And we can talk about that more later, but I think we're out of time now.
It's definitely an interesting question, and it's a really hard thing to do. So yeah, good question.